Am I supposed to be hearing something, Nicolas? Okay, I cannot hear anything.
Okay, I think Nicolas is in mute, but I think, well, Walter, can you start the presentation, I think?
Okay. And then
Yeah,
screen sharing
thank you.
too. Okay. Well, hello, everyone. I'm very happy to be here, and thank you to Nico for the invitation. I love this program of the webinars every week, talking about particle physics to especially Latin America, but everyone else. And so today I'm going to present, I'm going to start screen sharing I hope it is this one. Okay, and then I have to go. Okay, I'm going to talk about a work that I did with my collaborators in Tel Aviv University with Kosaku Tobioka, Lorenzo Baldi, and Tomer Volansky. And this was a painful project that lasted quite a long time. So finally it's out, and we gave it the name of relaxed inflation. And it has to do with some work that was introduced a couple of years ago by Graham and Kaplan and Rajendran, where they presented a novel solution to the hierarchy problem. So as we know, the hierarchy problem has to do with the fact that when you consider the standard model as an effective theory, then the mass of the Higgs is not natural in the sense that it's too small for the cutoff, that the natural cutoff that the theory should have. And there has been a very large variety or beautiful works for the last 3 or 4 decades of people presenting different types of solutions to this, and they go by the name of supersymmetry, extra dimensions, large extra dimensions, technicolor, twin Higgs, composite Higgs, and they are beautiful models and beautiful physics. Is that what we have learned with this? But the majority of these type of solutions, they require the introduction of new degrees of freedom at the electroweak scale. And now it's been many years, so several years of probing this energy scale at the LHC, and nothing has been found. So in view of this, these people proposed a solution where no new degrees of freedom are introduced at the electroweak scale, and instead the solution relies on the dynamics of a pseudoscalar field that is like an action that is coupled to a strong group similar to QCD, for example, that effectively produces a cosine potential, and of course that is coupled to the Higgs. And if this theory is going to be natural, then the mass of the Higgs should be naturally the size of the cutoff of the theory. So this lambda here is the cutoff of the theory. And then the Lagrangian written completely, or the potential of this, can be written in this way. And you see that there is here some effective mu term that can be either positive or negative depending on the value of phi. So the whole idea is that during inflation, although phi, in this case the pseudoscalar field, is not the inflation in the original model, the idea is that during inflation, phi is rolling very slowly. So you have a very flat potential. And there are 2 different regimes. One regime, this effective mu term is positive. So electroweak symmetry is exact. And then basically you have just that phi is rolling, and the wiggles from the QCD are not there, or the wiggles from the effective potential for the pseudoscalar field, because this guy is proportional to the web of the Higgs. But if the electroweak symmetry is exact, there is no web for the Higgs. So this term is actually not there. So that's why I didn't draw the wiggles here. So it's phi is rolling, it's slowly rolling. And then at some point, when this effective mu term becomes 0, then after that, electroweak symmetry is broken because the mu term is negative. Then you have like spontaneous breaking of the symmetry, and then the wiggles appear, and then you have the wiggles here. And then as the action or the relaxion now goes over the wiggles, at some point there is some condition that it has to be satisfied, and there is a minimum of the potential. Now you take this and this and that, and you take the minimum of that. That is basically given by this condition, and which can be more or less translated to this condition of the parameters. Then at that point, the relaxion is going to be stuck. It's going to stop. And then the question is where this happens. And if you look at the effective mu term at which, for which this happens, you see that it's naturally of the order of the electroweak symmetry, and of the electroweak scale. And then that sort of explains why the mass of the Higgs is so small, even if the cutoff of the theory is much larger. An extra condition that we need is that there is at least one wiggle between the point where the symmetry breaking happens and where the relaxion stops, and that is given by this condition. Now, already with these conditions that we have here, and with the fact that we are in inflation, but that phi is not the inflaton, there are several consequences that were found in this original paper. One of those has to do with the fact that because m is so small, the excursion of phi during all this process is going to be much larger than the Planck scale. So we have transplanckian motion, which is not ideal, but it's not something that it's not something rare. You find it very often in models of inflation. But anyways, it's one of the consequences. Another consequence is that there will be many e-faults. I mean, here, this doesn't say much, but to give you an order of magnitude, in their paper, they found that you should have at least 10 to the 45 e-faults. So that's quite a lot. And the third consequence has to do with the strong C-prey problem. And it's basically the fact that due to this, the axion was introduced in physics because we wanted to solve the CP problem, the fact that we measure a theta parameter that is very small. But here, if I get stuck at some point, in a generic point here, then it gets an expectation value that is of order of f, and the effective theta parameter is going to have a value that is of order 1, and that is not, I mean, that basically reintroduces the problem that the axion solved in the first place. And then the fourth issue is that the cutoff, after you take into account these constraints, and that the energy density of stored in this pseudo-scalar field cannot be larger than the energy density of the inflaton, because the inflaton is what is driving the dynamics of the universe during this epoch, then that imposes that the cutoff has to be smaller than 10 to the 8, 10 to the 7. There is a GeV missing here. So it's large. It's much larger than the electroweak scale, yes, but it's not so large. So what when we read this paper and we were discussing in Tel Aviv, then we wonder, can we do better than this? But can we do better? We mean, first, can we actually obtain some Planckian motion? So instead of transplanckian excursions? And the answer, I can give it later, but I can give it now too. The answer is no. So then we looked at for us, the most important issue is that the CP problem issue, they knew in the original paper, of course, and the way that they solved it is to introduce an extra strong group with some new fermions that are hidden. So and then this theta is not the theta of the QCD, and that avoids any issue with QCD. But for us, the most important issue that has to do with naturalness is the fact that we don't have a large enough cutoff. I mean, what happens? I mean, can we make the cutoff as large as the Planck scale? And this is going to be our main goal in the paper. But with that, it comes also a very, at least for us, a relevant question, and is, can we make the inflaton and the relaxion the same field? Instead of playing with two fields at the same time during inflation, can we just have one that plays two roles, the inflaton and also the relaxion? So that's what we want to do. And then on our way, we found that there might be something important that is already present in this toy model, but that was maybe overlooked, or the people didn't pay enough attention to that. And is that this place here is important in the sense that it's a place where particle production can happen due to the fact that here there is an enhanced, this is what they call an enhanced symmetry point, because the mass of the Higgs becomes 0. When we started looking at particle production, we realized that particle production during this process can be relevant. On one hand, to reheat the universe. If we want phi to be the inflaton, then we need to think about how to reheat the universe. But on the second hand, it might provide dissipation that helps for the slow roll, especially at the end of inflation. And then we don't have to rely so much on the flatness of the potential. So after going around many times, we arrived to proposing a relaxion model where the inflaton is the relaxion, and now it's coupled to a U1 photon. For now, I don't want to specify if this photon is the standard model photon or a hidden photon, but it's just an Abelian, it's a massless. We have a massless vector gauge field, and it couples to the relaxion f tilde term. And this model was studied years ago by Amber and Sorbo. And then so when we write this model, then we want to solve the equation of motion that we can write in this fashion. Here, this is the conformal time, and I have introduced some redefinition for the velocity weight by the Hubble scale, that is, or the Hubble parameter that is given here. And this E dot B comes from this term, where this brackets here, they just refer to the Hart approximation, where we are integrating over these guys are written in momentum space, and you are integrating over the phase space. And so we want to solve this too, and of course this, you can see that looks just like the standard equation of motion for the inflaton, except that now we have an extra term here. And this is the equation of motion for the photon, of course, with the two polarizations. But notice that here, this term that is some sort of efficient, effective frequency, it has a peculiarity. For some small, for very low values of k, of the momentum, for some values, you have that this frequency, that is frequency squared, is going to be negative. And that would imply that there are some modes that become tachyonic. And this is something that is seen in many places in particle production during cosmology, that there is some non-perturbative production of particles that is exponentially enhanced due to the tachyonic instability of these modes. But notice that it's just one of the modes, right? The one, I mean, in this case, in this notation, A minus. So, and indeed, a solution to this equation of motion for the tachyonic mode when psi is large enough, when it's larger than 1, is that the modes grow exponentially, which implies that the energy density stored in these photons that are being produced grows also exponentially. And this term that will then back react into the equation of motion for phi is also growing exponentially. So so now we want to exploit this exponential production of photons to see what we can do in terms of the relaxion and reheating the universe. So with this, I can give you what our picture is. We have several regimes here. At the beginning, we have the slow roll. So we have a very flat potential that is written here. And here we have just the linear approximation of the potential. So in the beginning, we have that the symmetry, due to the mu term being positive, the electroweak symmetry is exact, and we are just slowly rolling. At some point, the effective mu term becomes negative, and then the wiggles appear, the wiggles from the cosine potential. But then we still we are producing photons, but we haven't produced enough. So during this regime, the equation of motion just looks exactly like the slow roll regime that we studied in kindergarten, where just these two terms equal to 0. We can ignore the second derivative, and we can ignore the production of photons here. But at some point, the photons are produced enough, and then it's actually these two terms that are important. And then I'll show you how what the solution to the equation of motion is for this case in a sec. And then at some point, there is enough energy stored in photons such that it actually is larger than the energy stored in the inflaton. At that point, the photon starts driving. They start driving the dynamics of the universe, and we call that the reheating. And there is some relaxation period here. At some point, the inflaton now, the relaxion, stops. And here it's crucial that we will have to add a constant to the potential such that we tune the cosmological constant in the same way that you do in hybrid inflation or other models of inflation. You just tune the cosmological constant to be the observed value of the cosmological constant. And then that's where our dynamics ends. So in the first regime, we have slow roll. We define the standard slow roll parameters. There is nothing new here. It's easy to satisfy for the small values of the parameter m that we had in the model. But I won't go into details here because this is a standard story. The important thing is that at some point, this regime is what is going to be relevant, because we have produced and we keep producing enough photons. So here the equation of motion leads to a solution where psi, that remember that it's parameterizing the velocity or the speed of phi, is just growing exponentially. So here you can see how we go from one regime to the other. Initially you are growing. I mean, you are slow rolling, but you are sort of speeding up a little bit. But at some point, when psi is of order 10, 10 to the 1, we go from the regime 1 to the second regime where now the photons are the ones that drive the dynamics and the slow roll. And it's actually even more dissipative than the slow roll from the flatness of the potential. And phi and the velocity is pretty much constant. This psi evolves only logarithmically. And then at some point we want to reheat. There are several constraints here that were studied previously by Sorbo and company on one hand and collaborators of Peloso on another side. And is that this is incredibly nice that we have so much dissipation from the photons, but then there is a problem with the generation of the fluctuations, the curvature fluctuations during inflation. Due to if these guys start dominating the dynamics early enough, and by early enough I mean many e-folds before you end inflation, then you generate very large fluctuations, and then these fluctuations not only will be incompatible with the size of with the scale of the power spectrum measured in by CMB experiments, but also there will be many overdensities that will collapse into primordial black holes, and they will create an abundance that is incompatible with what we see today. So if we want to avoid if we want to evade these constraints, then we need to require that this transition here doesn't happen many e-folds before UN inflation, and that's why we have this transition in our case. We're going to set up such that it happens not earlier than 7 or 10 e-folds before we end inflation. So the perturbations that we see in the CMB, they are in this type of low scale inflation, they are generated at 30 or more e-folds before we end inflation. So that's why the fluctuations that you generate during this regime that are very large, they won't show up in the CMB, nor will create primordial black holes that are too large and incompatible with what we have measured. So so we have reached this point where we have to reheat. So we have to reheat the universe, and this is where actually, for us at least, things became more interesting, because you have an exponentially large number of photons, but they have a peculiarity. The momentum is very small. You have a huge occupation number with a very low momentum, and that's what we call in physics a classical electric field. So indeed, you're producing lots of photons, but effectively they are not behaving as a gas of quantum photons, quantized photons, but they are just behaving as a classical constant electric field. And then the way that we reheat the universe is by looking at a non-perturbative effect that exists in quantum electrodynamics, that is the Schwinger effect. When in the presence of a very strong electric field, you can create, out of the vacuum, you break the vacuum, you create a positron and an electron, and the rate is unsuppressed once the electric field is much larger than the mass of the electron squared. So in this case, then you transfer a lot of the energy of the electric field into the electrons, and then the electrons are also accelerated by the constant electric field itself, and they will start colliding, and then they will thermalize. And this is a type of reheating that for us it was more like a surprise in the process, and we hadn't seen before, studied in the literature. And when the energy that is transferred into the electrons is of order of the energy that was in the photons, then we have a thermal bath that will give us a temperature of the order of lambda naught, that is the size of the potential in the small wiggles, basically. So this is something similar to the lambda QCD. And so this so far sounds very good, except that there is an effect that we hadn't taken into account here, and is that if this photon is the photon from the standard model, then they will thermalize very quickly with the photons that are being produced. And then once you have a thermal bath, then there is some screening mass, some Debye mass for the photons that will kill the tachyonic instability, and then you kill the particle production of photons, and then you are not reheating the universe. The maximum, in this case, the maximum temperature that you can obtain for the reheating temperature is of order of the mass of the electron. That is not enough for BBN. So the way that we went around this was to introduce a dark photon instead that has a tiny coupling to the electrons, that here we parameterize with this kappa. I mean, the full coupling, we just call it E kappa. And then in this case, this guy is coupled weakly enough to the electrons such that they don't thermalize fast enough, the photons. The electrons will thermalize among themselves, but not with the dark photons. And then when the electric field, because we can produce very large electric fields, there is no problem with producing a much larger electric field than in the case where we had the photons at the standard model. And then we will still be able to use the Schwinger mechanism to produce pairs of electrons and positrons, and then we need to require first that the electrons, that the photons don't get a thermal mass that is given by this condition here, but also we need to make sure that we don't suppress the Schwinger effect in the sense that the Schwinger, this rate has to be fast enough so that that we can transfer the energy. And then during this time, the relaxation is still slowly rolling, and at some point we reach again this condition that we mentioned at the beginning, where we stop, and then we end our dynamics. But notice that, unlike in the first in the original model, here the relaxation of the stopping of the relaxation happens after you reheated and after you exited inflation. And so then with all these dynamics, then we can look at all the constraints. We have 6 parameters in our theory. We have the coupling of the relaxation to the photons. We have the size of the wiggles. We have this is also the characteristic scale of the decay rate of the relaxation, and then this was the slope of the potential, the flat potential, the cutoff of the theory, and the coupling of the dark photons to the electrons. And on one hand, we need to have, so since we want to have the cosine potential, we need F to be just larger than the cutoff of the theory. And this constraint came from the fact that we needed to have at least more than one wiggle between the symmetry breaking point and the stopping of the field. And this one came from the fact that we need to have a small enough, flat enough potential such that you can stop at some point when this condition is satisfied. And this condition comes from what I mentioned, that you want to have the second regime, the photon production regime. We want to enter that regime not too early, so that we are consistent with CMB constraints, but also we want to enter at some point this regime. We don't want to enter this regime before phi stop, after phi should have stopped. So it shouldn't be too late. Basically, usually, I mean, we require that we enter this regime before inflation ends. So at least a few e-folds of inflation happen while the photons are driving the dynamics. So all this, basically, all this together, they give us this region of the parameter space. These lines, the red lines, are the ones that are the values of the coupling constant of the coupling between phi and the photons given by this condition here. And this is the type of heat temperatures that we can obtain, and we can see that we can even get TV reheat temperatures, so that's nice. And this condition of the not Schwinger effect comes from the fact from this inequality, because this, if you see, you take this guy and this guy, you obtain an condition on lambda naught, and there is some factor of psi missing here that basically gives. That's why this is a diagonal and not just a vertical line. But anyways, it's a condition that looks like this, up to a factor of psi. And then there are some conditions on experiments that are looking for fifth forces and that were presented in this paper by a group from Weizmann, and constraints from astrophysics, in the sense that if this coupling between phi and the Higgs is relevant enough, then, or large enough, then you would obtain some extra cooling for stars and supernova, and that enters here. And then you could produce these guys in beam damp experiments, so that enters here, and so on. So that is where these two constraints come from, and this comes from the fact that the lambda wiggle, that is lambda naught in this case, should be larger than the. Oh, this is actually should be smaller than the electroweak scale that we call here just MW. So this is what we did. We think that this relaxion that has been around for 2 years now is a very interesting mechanism, and now we were able to incorporate the features of inflation, and in some ways it sort of brings back into the attention what has been called in literature action inflation, because there were many constraints from action inflation due to the perturbations and everything, but this is a nice realization of action inflation, and where now the action is not only the inflaton but also the relaxion that stabilizes the mass of the Higgs. And notice that since the only condition is that lambda is smaller than F, we can have lambda, that is the cutoff of the theory, as large as 10 to the 17 GeV. So that is very close to the Planck scale, just one order of magnitude below, and that is many orders of magnitude above the original model that was only like around here. So we indeed were able to obtain a very high cutoff. That was our original purpose. And then in our way to reaching this point, we realized that particle production, especially these tachyonic instability features, that this is crucial in reheating, of course, and can be used also as for a dissipative effect at the end of inflation, because back reaction of this energy density into the dynamics of the relaxion. And then there was the nice reheating process that we sort of bumped into by using the Schwinger effect. That if you use it carefully without, taking into account the thermal effects, you can use it to reheat the universe. And now we are working on like more specific details of this, and we hope at some point we can present it later this year. And that's it. Thank you very much. I don't know if you guys actually were listening, but let me see. What do I do? Okay.
Thank you, Walter. That was great.
Okay. So you guys listen. I don't know if people were hearing that.
Yeah.
No, everybody heard. The only problem was that Nicolas' microphone died. So I'm going to. So he did an introduction for you, but it's silent.
Okay.
So what I'm going to do is I'm going to open the floor for questions from the audience here, and then I'm going to go over the Twitter and also the Google Hangouts page to see if there are any questions from the audience that has been watching your seminar and are not here. So, but let's first, let's just ask Walter any questions that we might have for him. So I'm opening the floor for anyone here. Okay, so I think Nicolas, whose microphone is dead, has a question, and so he's gonna type it up, and I'm gonna just say it back to you. Go ahead, Nico. Okay, his question is basically from the introduction. Why do you want to avoid a not too large cutoff?
Well, that is the purpose of presenting a solution to the hierarchy problem. If there is no new energy until up to Planck scale, and no new degrees of freedom up to Planck scale, then you should. Of course, 10 to the 8 GeV cutoff is a nice enough cutoff if you want to explain why the mass of the Higgs is not 10 to the 8 but 10 to the 2. Mm-hmm. But ideally, it would be nice to have. So what happens then with God theories, for example? Let's suppose that we believe in gods. So then the relaxion is the original relaxion model is not good enough. It's not efficient. It's not good for stabilizing the mass of the Higgs if there is energy, if there are new degrees of freedom at 10 to the 16 GeV. So we wanted to just push it as large. The higher the cutoff, at least from our point of view, the more efficient and the nicer this construction is. If it is something whose goal is to stabilize the mass of the Higgs, then the higher the cutoff, the better the model, no?
Yeah, in essence, you would want the cutoff to be the Planck mass, no?
Exactly. That would be, yes. We couldn't reach the Planck scale, but 10 to the 17 is good enough.
Yeah, well, yeah, 10 to the 17 is pretty high up there. I do have one question really quick. What happens, how do you deal with this cosmological constant tuning? Isn't that just another tuning?
Yeah, this is not different from the cosmological constant tune, the tuning of the cosmological constant that you do in other inflationary models. You always need to make sure that at the end, the vacuum energy is zero. Pretty much zero. So that's why in any flat potential that you write for any inflationary model, at least for most of them, you have to set the zero at the end of inflation, right? The zero of the potential is at the end of inflation. Otherwise, you will stuck with cosmological constant. So there is some quick analysis that you can do because it's true that there would be some worry that what we're doing here is sort of cheating because we are tuning the cosmological constant in order to tune the weak scale. So it's like we are double tuning, but it's not deep. In this case, it's not. It has nothing to do with the tuning of the electroweak scale. Mm-hmm. It's just the normal tuning. And if you take one of these measures of like how much tuned the model is, This is basically as tuned as any other model of inflation.
Okay.
So in this case, it's not like we are transferring or even increasing the tuning. It's just the normal tuning that we have in inflation.
But isn't it? Do you think it's? I mean, they're totally unrelated. But if they were related, wouldn't that be an actual kind of?
Yeah. So at the beginning, for some time, we actually thought that they were related. That by tuning the cosmological constant, we are setting the electroweak scale, and in that case, it would be even better because. Yeah, but at the end, we realized that that is not what's happening. At some point, we were excited because we were saying, okay, good. So give me a solution to the cosmological constant, and then tuning the cosmological constant will give you the solution to the hierarchy problem. But that is not what's. I mean, yeah, it's not what is happening here.
Okay.
It would be nicer, but it's not.
Do you think are you going to explore any models which can accomplish that, or is it just an?
Yeah, I think that I'm not allowed to say. I'm not allowed to comment on that.
Okay. All right.
Sorry.
Okay. So now I have two questions from the audience here watching your seminar. Well, the first one is, what are the constraints for the psi field? For psi? No, I don't know the psi.
So, yeah. Okay. Psi is a redefinition of the velocity. Psi is phi dot divided by f times h, where f is the coupling of phi to the photons, and h is the Hubble parameter. The constraints are, well, there are no constraints except that during the slow roll, of course, psi is incredibly tiny because phi, there is no much kinetic. I mean, we are in slow roll regime, so it's very tiny. And then it does grow, but it won't go beyond of order 20, because after you enter and this happens that it gets of order 20 when we enter the photon driven dynamics. But because it grows logarithmically, then it won't grow much larger than 20. And then at some point we'll just reheat the universe, and phi will stop, so just psi becomes 0, and there is no that's the end of the story for psi.
Okay. And the second one, are there any constraints on non-Gaussianities?
Well, the constraints on non-Gaussianities are basically the same that are present in the axion inflation papers, but here they actually don't. Since we are entering the photon-driven dynamics, only in the last 5 e-folds, they won't affect the Gaussian or non-Gaussian distributions of the perturbations that we see in the CMB, because these guys are going to be generated. In this case, we are talking about low-scale inflation, and in low-scale inflation, the CMB, what we see, the fluctuation that we see in CMB, they come from like 30 to 35 e-folds before the end of inflation, not 60 like in high-scale inflationary models. So far, I mean, we haven't explored deeply this question of the non-Gaussianities. We didn't compute the power spectrum coming from this part from when we have the photon-driven dynamics. But the most constraints that apply to axion inflation would apply to this inflationary model if the photon production regime, when this regime is dominant, if you enter this regime much earlier than this, but then by entering so late, we are evading this. So in our case, we don't care about this regime so much for the inflation part, but for the relaxation of the electroweak scale part. But this happens anyways after the end of inflation, so we only care about entering this regime just in a couple of folds before we end inflation, and then this won't affect the CMB with non-Gaussianities.
Mm-hmm. Would you mind showing your plot again, the chi versus the psi versus the e-folds plot?
Yes, I don't mind. No, I don't mind. Can you see? Can you see?
Yeah, I can see your screen.
Okay. Here is echo. Yeah, so see, for example, here, so you psi is growing indeed. This is the velocity, but it's growing not only because the velocity is phi is speeding up just a little bit, but also the Hubble, because we are going down. Hubble is decreasing, so psi will just grow. But then in the, like for example, in Sorbo's paper, so Amber and Sorbo, and some papers by Peloso or a few other groups that have explored this regime would happen like in 30 EFOLs, for example, like around here. But then in that case, you produce the power, the size of the power spectrum, the scale of the power spectrum is like the fluctuations are 4 orders of magnitude larger than what you see in CMB. So in that case, that's why many people discarded this type of models early in the, like a few years ago. But because they were trying to avoid having a flat potential, but so they wanted to have just like a very steep potential or an arbitrarily steep potential, and then the dissipation would come from the photons, right? I mean, if photons are giving you dissipation, you don't care about the flatness. But then the problem is that if you are relying only on the dissipation for the rolling of the inflaton during the relevant EFOLs for CMB, then this is ruled out, basically.
So Nicolas says, okay, so I guess I kind of probably answered this question. So the flat regime corresponds to the epoch when the dark photon dominates then?
No, you have to say that again.
The flat regime, the regime number 2 in your plot.
Yes, exactly. Okay. When it's this regime, right, where the solution is logarithmic. See?
Yeah.
So it just goes, right. So that's why I call it regime 2. Is this regime here? Yes.
Okay, and then we're getting some more questions here. So one question is, so from the audience here, the mechanism breaks parity symmetry. Are there any sizable signals on this model from you can put on the CMB?
Well, again, if the CMB is if the fluctuations in the CMB that generate around here. If we were already in the second regime here, like for example in Sorbo's paper again, in that case, yes, there should be, because you are generating one polarization more than the other, so you should see some breaking of the parity there. So you will see one polarization more than the other. But in this case, again, the CMB that we see today, the fluctuations coming from this regime, we don't see them in the CMB. They don't show up in the CMB. Okay. Unfortunately, it would be nice if we had this parity breaking show up in the CMB, because that would be an observable one more observable for the theory.
Definitely.
But unfortunately, no. We can't see it.
All right, and one last question from Vinicius Santos Terra. The temperature on the end of the reheating period,
yes,
is it sufficient to suppress the creation of monopoles?
It's sufficient to suppress the creation of monopoles. I don't know how to answer that question.
Okay.
Monopoles coming from the dark U1?
Yeah, let's see. Let me ask Vinicius which monopoles he refers to. Okay, let's see. So we'll wait till Vinicius rephrases his question, but is anyone here in the audience, would anyone like to ask another question? So you have additional fermions in your model?
Well, so we will need additional fermions, but they can be very heavy in order to generate, because now we are talking about these dark photons.
Yeah.
We need anomaly to couple phi to the photons.
In
addition, we have the strong dynamics. I mean, if you want to avoid the strong CP problem, then you need a strong a dark strong group.
Yeah, But so which I mean, I don't know if you said this already, but Can you probe this in the LHC?
Well, there are constraints. There are constraints on this coming from. So there are constraints from not finding in the LHC that is included here in the. Oh, where am I again? Oh, here. That is included in this orange. Yeah. So what is it? This orange region here, but I think that the production prospects in the LHC are quite limited because of the smallness between in the coupling between these guys. I mean, this value is very small. It's natural because once m goes to 0, then you recover asymmetry because for the pseudoscalar, but it's very small.
So here's a crazy question. So you're basically saying that the inflaton is this axion, right?
Yes.
Okay. How? So can you probe this model through any topological effect in neutron stars or sort of mediums that are really strongly coupled and topological in a sense? I don't know, like, I mean, if it's an axion, then it has some sort of topological coupling, right, to matter.
Yeah, well, the FF tilde.
I think we can discuss this later, but I mean,
Yes.
I'm interested in this topological effect, so probably we could talk about it.
Yeah, so yeah, you can think about because this guy is a pseudoscalar. Then there are many things that you can think of doing with this that people have done with actions, right? But this is a very different action, right? Because F can be much larger, but also, I mean, the effective mass of this guy is incredibly tiny. I mean, if you take like the effective mass of these guys is incredibly tiny. But anyway, we can discuss this later.
So I think Vinicius hasn't rephrased the question. So maybe perhaps we can follow up with you later on. So if there are no more questions, I'm gonna just give you a little. I'd like to give you a little brief intro that probably no one heard. So just to remind everyone, Walter is a graduated from the University of Texas at Austin, cool town, and he will now be a faculty at Colgate University in New York, right?
Yes.
And so we will have him teaching next generation of undergraduates and doing research with them, and he will be also collaborating with people in Cornell. Walter he's finishing a postdoc in the University of Tel Aviv, and I met Walter a while ago in Argentina during one of my favorite summer schools that I've attended. So, and I've also I've had the pleasure of working with Walter in a paper. So I want to thank you, Walter, for this really nice seminar.
No, thank you guys. It's great that we have this space.
Yeah, and if you can pass around this to anyone else who would like to talk, just send them ask them if they want to participate. It will be nice to have many other speakers from around the world. So with that, I'm going to close today's webinar, and we hope to see you all next time. Thank you, Walter.
Gracias.